July 1st, 2025, a telescope in the Rio Hurtado Valley of Chile sees something that shouldn't be there. The Asteroid Terrestrial Impact Last Alert System, ATLAS, catches a fuzzy dot moving wrong. Too fast, wrong angle, not bound by our sun. Within hours, observers worldwide lock on. By the time the Minor Planet Center confirms it, the math is brutal. This thing is traveling at 245,000 kilometers per hour on a hyperbolic trajectory. Not just fast, escape velocity. This is 3I Atlas, the third confirmed interstellar visitor in human history. And it's carrying a chemical secret that rewrites what we thought we knew about comets from other star systems. Then 2I Borisov in 2019, a proper comet, carbon monoxide rich, looked almost normal except for its origin beyond the stars. Now 3I Atlas, bigger, brighter, active, and completely wrong in the best possible way. This isn't just another space rock drifting through. This is a messenger carrying the chemistry of a distant planetary system, and every telescope we can aim at it is racing against time before it vanishes forever into the void. If you value documented astronomical discoveries and real spectroscopic evidence like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Martin Cordner's peer-reviewed study published in the Astrophysical Journal, Letters on September 10th, 2025, analyzing James Webb Space Telescope NIR-SPEC data captured on August 6th, and from Carrie Lias's SphereX, observations published in research notes of the American Astronomical Society in August 2025. These aren't popular science summaries. These are the actual spectroscopic measurements, production rate calculations, and isotope ratio analyses from the instruments themselves. Now back to the information. The NIR-SPEC integral field unit splits incoming light across 0.6 to 5.3 micrometers, 30 by 30 array. Each pixel captures a spectrum. When the data downloads and the team runs the analysis, they see something that makes them double-check their calibration. The spectrum is dominated by one molecule, carbon dioxide, not water. Carbon dioxide. The main emission peak at 4.3 micrometers is so strong it overwhelms everything else. Water vapor shows up weak. Carbon monoxide barely registers. The ratio? 7.6 to 1. Carbon dioxide to water. The highest CO2 to H2O. Mixing ratio ever measured in a comet. 6.1 standard deviations above the trend for long period in Jupiter family comets. This isn't an outlier. This is a different class of object. Let's break down what the instruments actually detected, because the details matter. NIR-SPEC captured low vibrational fluorescence emission, molecules excited by sunlight releasing photons at specific wavelengths. Carbon dioxide shows its main new 3-band at 4.3 micrometers. Strong. Bright, extended across the entire 3 arcsecond field of view. Water shows weak emission at 2.7 micrometers from the new 1 plus new 3 combination band. Carbon monoxide appears faint at 4.7 micrometers. The team also catches carbonyl sulfide at 4.8 micrometers, and water ice absorption features at 3 micrometers and 4.5 micrometers. But carbon dioxide dominates. Production rate, 129 kilograms per second. Water, 6.6 kilograms per second. Carbon monoxide, 14 kilograms per second. The water mass loss rate is only 5% of the carbon dioxide output. For comparison, normal comets at this distance blast out water as their primary volatile. 3I Atlas is backwards. Spectrally integrated flux maps show carbon dioxide extending smoothly in all directions, with enhanced outgassing toward the sun. The dust map at 1.2 micrometers reveals a plume-like feature pointing sunward, slightly north of west, with a weaker feature northeast. The carbon dioxide map shows a bright, diffuse cloud spanning the full IFU boundary. Water and carbon monoxide, weak, consolidated near the nucleus, not filling the coma like CO2 does. The asymmetry suggests the nucleus is rotating, venting gas preferentially from sun-facing regions as volatile ices sublimate. Standard comet behavior, but the chemical inventory is anything but standard. SphereX observations between August 8th and 12th, 2025 paint the same picture but add detail. SphereX, spectrophotometer for the history of the universe, epoch of ionization, and ICES Explorer, uses imaging spectrophotometry across 0.75 to 5 micrometers. When the SphereX team maps 3I Atlas at specific emission wavelengths, they find water and carbon monoxide essentially absent. Upper limits only. But carbon dioxide? A massive symmetric cloud extending at least 348,000 kilometers from the nucleus. The CO2 gas production rate calculates to 9.4 times 10 to the 26th molecules per second. The Coma brightness declines with projected distance to the power of -3/2 out to at least 30 pixels. That translates to a CO2 density falling off with 3-dimensional radius to the power of -2.5. Steep decline, long lifetime. The photodissociation lifetime for carbon dioxide at 1 AU is 135 hours. At 3.2 AU, that scales to roughly 1,300 hours. The observed coma size suggests CO2 molecules survive roughly 700,000 seconds before breaking down. The physics checks out. No carbon monoxide coma, conservative 3 sigma upper limits, 1.5 times 10 to the 26th molecules per second for water, 2.8 times 10 to the 26th for carbon monoxide. Compare those to the massive CO2 production and you get the picture. This comet is venting carbon dioxide almost exclusively. Carrie Lisa, Johns Hopkins astronomer on the SphereX team, puts it directly. 3I Atlas lacks carbon monoxide and shows a carbon dioxide coma with a water ice nucleus, meaning it was well baked and boiled before being ejected from its parent solar system. The light volatile ices, carbon monoxide, nitrogen, methane, those boil off at low temperatures. 40 Kelvin does it. Anything beyond Neptune's orbit can lose those ices over time. But carbon dioxide and water, those need heat, real heat, hundreds of Kelvin. 3. I Atlas lost its light volatiles somewhere, sometime before it got kicked out into interstellar space. Sub-millimeter observations by ALMA, UV spectroscopy by Swift and Hubble, optical imaging from dozens of telescopes. Borisov showed enriched carbon monoxide relative to water, high CO to H2O ratio. It looked like a very young Kuiper Belt comet, volatile-rich, pristine. 3, I Atlas, is the opposite. Low carbon monoxide relative to both water and carbon dioxide. High CO2 relative to water. It looks evolved, processed, thermally altered. If you line up the 2 interstellar visitors we've characterized, they span opposite ends of the comet chemistry spectrum. Borisov, carbon monoxide dominated young cold formation. 3, I Atlas, carbon dioxide dominated evolved warm history. Hartley 2 is a Kuiper Belt comet that fragments and spits out large chunks of CO2 ice. Lots of carbon dioxide, no carbon monoxide. Water only appears when it gets close enough to the sun for water ice sublimation to kick in. Sound familiar? Hartley 2 formed in our outer solar system, got thermally processed over its lifetime, lost light volatiles, now outgasses CO2 preferentially. 3I Atlas shows the same signature, different origin, same evolution. This suggests 3I Atlas went through similar thermal processing in its home system, or during its journey through interstellar space, or both. Carbon dioxide ice forms beyond the CO2 frost line in protoplanetary disks. That's the distance from a star where temperatures drop low enough for carbon dioxide to condense into solid ice. For a sun-like star, that's roughly 10 to 15 astronomical units out, beyond Jupiter's orbit, but not as far as Neptune. If 3I Atlas formed close to this boundary, it would naturally contain lots of CO2 ice. Alternatively, if it formed farther out in a colder region but then migrated inward, got heated, lost its light volatiles, and subsequently got ejected, you'd also get a CO2-rich object. The JWST data can't distinguish between these scenarios, but both require specific thermal histories. Another possibility, radiation processing. Cosmic rays. 3I Atlas has been traveling through interstellar space for a long time. Dynamical modeling by multiple teams suggests an age of 3 to 11 billion years based on its velocity relative to the local standard of rest and its likely membership in the Milky Way's thick disk. The thick disk is the older, more metal-poor component of our galaxy's stellar population. Stars there average 7 to 10 billion years old. If 3I Atlas formed around a thick disk star and got ejected early in that system's history, it's been drifting through the galaxy for potentially 7 billion years or more. That's longer than our entire solar system has existed. During that time, cosmic ray irradiation could alter surface ices. High-energy particles slam into molecules, break bonds, create new compounds. Stephanie Milam from NASA Goddard, who worked on the JWST observations, suggests 3I Atlas may have developed a cooked shell on its surface where CO2 ices were created through irradiation chemistry. That excess carbon dioxide now vents as the sun heats the nucleus. The nickel detection by the Very Large Telescope on August 23rd supports this. Nickel tetracarbonyl is highly volatile, breaks apart easily in UV light to release nickel and carbon monoxide. If the coma contains nickel from decomposing nickel carbonyl compounds, that could partly explain the high activity level far from the sun. If you assume all the 1 micron flux comes from scattered sunlight off a spherical nucleus with a 0.04 albedo, you calculate a radius of 23 kilometers. That would make 3I Atlas massive, 1,000,000 times more massive than 2I Borisov. That makes no statistical sense. We should have found thousands of Borisov-sized objects before stumbling on a 46-kilometer interstellar rock. The Atlas survey ran for over a decade. The expected flux of interstellar objects based on stellar ejection rates and galactic density doesn't support that scenario. The alternative, most of that 1 micron flux comes from coma dust, not the nucleus. Carrie Liss's analysis suggests 99% or more of the measured continuum flux is from dust grains, many of them likely CO2 ice fragments. That would put the actual nucleus size below 3 kilometers in diameter, consistent with Hubble imaging constraints of 0.32 to 5.6 kilometers. Probably less than 1 kilometer. Small nucleus, massive coma, that ratio works. JWST detected 13 CO2, the heavy carbon dioxide isotope, at 4.4 micrometers. Weak signal, partially obscured by dust and other gases, but present. The 12C to 13C ratio appears broadly similar to Earth's value and to ratios measured in solar system comets. That suggests 3I Atlas, formed in an environment with carbon species similar to our own protoplanetary disk. Not exotic, not alien chemistry, just cometary material from another star system that underwent different thermal evolution. The building blocks are the same, the history is different. Water ice shows up in the JWST spectrum as absorption features at 3 micrometers and 4.5 micrometers. OH, stretching mode, and lattice vibrations of solid water ice in small grains, probably less than 10 micrometers in size. Icy dust grains in the coma, not just gas. Spherex also detected strong water ice absorption in its combined spectrophotometry. But here's the puzzle. Solid water ice is present, but water vapor is weak. Sublimation is happening, but slowly. The production rate of 6.6 kilograms per second is low for a comet at 3.3 AU. Why? 2 possibilities. 1, the nucleus has an unusually thick, insulating crust or mantle that inhibits heat penetration. If the surface layer is low thermal conductivity material, refractory dust, processed organics, then heat from sunlight can't efficiently reach the water ice below. Carbon dioxide and carbon monoxide, being more volatile, sublimate at lower temperatures and vent from shallower depths. Water stays locked beneath the surface. 2, the nucleus is intrinsically water poor. Maybe it formed in a region of its parent disk, where water ice was less abundant relative to CO2, or maybe it lost water preferentially during thermal processing. Both scenarios predict that as 3, I Atlas approaches perihelion in late October 2025 at 1.4 astronomical units, just inside Mars' orbit, water sublimation should ramp up significantly. The sun's heat will penetrate deeper. Water production rates should spike. We'll see if a large water coma develops to match the carbon dioxide envelope. This script uses peer-reviewed sources. Martin Cordner's JWST study submitted to Astrophysical Journal letters with co-authors from NASA Goddard, Catholic University of America, Auburn University, and multiple international institutions, and Carrie Liss's Spherex analysis published in ResearchO. Notes of the AAS in August 2025. Both papers provide raw production rates, mixing ratios, flux measurements, and error bars. This is documented science. Now back to the details. First Hubble images on July 21st showing a bright coma and dust features. Spherex observations August 7th through 15th capturing the extended CO2 cloud. JWST on August 6th, providing the most detailed spectroscopic breakdown. Very large telescope observations on August 23rd detecting nickel emission lines and cyanide gas. All this data captured in less than 2 months, while 3I Atlas was inbound between 4 and 3 AU. The observational window is closing. By late October, it reaches perihelion and passes too close to the Sun for Earth-based observation. Solar conjunction on October 21st means the comet is hidden behind the Sun's glare from our perspective. It reemerges in December, outbound, already departing the solar system. By then, most of the volatile material will be gone, sublimated away during the perihelion pass. What we're seeing now is likely the best data we'll ever get, hence the urgency. Every major telescope that can observe infrared wavelengths is scheduling time. Hubble will do ultraviolet spectroscopy in November to measure sulfur to oxygen ratios. JWST is scheduled for follow-up observations in December. The James Clerk Maxwell Telescope detected hydrogen cyanide on September 7th at a production rate of 1.5 times 10 to the 25th molecules per second. The VLT continues monitoring nickel and cyanide emission lines as they strengthen with solar heating. ESA's Mars Express and ExoMars Trace gas orbiter will observe from Mars orbit on October 3rd, when 3I Atlas passes roughly 30 million kilometers from the red planet. We're throwing everything at this object while we can. Let's put numbers on it. Typical Jupiter family comets at 3 to 4 AU show CO2 to H2O ratios around 1 to 1 or lower. Water dominates. Long period comets from the Oort cloud show similar ratios with occasional CO2 enrichment, but rarely above 2 to 1. The outlier is C 2016 R2 Pan-STARRS, a highly unusual comet with extreme CO enrichment and modest CO2. Excluding that statistical freak, 3I Atlas sits 7.6 to 1, 4.5 sigma above the trend. That's not variance, that's a different population. The carbon monoxide to water ratio at 1.4 is actually normal, which makes the situation even stranger. Why is CO2 so enhanced while CO stays ordinary? The sublimation temperatures give a clue. Carbon monoxide sublimes at around 20 to 25 Kelvin. Water ice sublimes efficiently above 170 Kelvin. Carbon dioxide sublimes around 60 to 70 Kelvin. It's the middle child. If 3I Atlas spent time in an environment where temperatures hovered in that range, warm enough to bleed off carbon monoxide, cool enough to retain water but perfect for accumulating or preserving CO2, you'd get this ratio. Or if surface irradiation created new CO2 from other carbon compounds while light volatiles escaped, same result. The data points to thermal processing, but the exact mechanism remains uncertain. The sunward dust plume in the JWST 1.2 micron map suggests a jet or active region venting material toward the sun. The carbon dioxide spatial distribution shows slight azimuthal variation with a minimum toward the north, likely from a combination of Coma substructure and optical depth effects. Close to the nucleus, CO2 becomes optically thick, so much gas that it starts absorbing its own emission, making it harder to see the full production. Farther out, the gas expands, thins, becomes optically thin again. The models account for this. The best fit production rates come from extracting spectra in 4 spatial regions: a central circle 0.625 arc seconds in radius, then 3 successive partial annular sectors, each extending another 0.625 arc seconds out. Fitting those curves gives you production as a function of distance from the nucleus. For carbon dioxide, production peaks near the nucleus and drops steeply. For water and carbon monoxide, production is concentrated very close in, suggesting these gases sublimate only from the hottest surface regions. The math is consistent with a rotating nucleus, with active patches on the day side, venting gas as it spins. The trajectory tells you where it came from in a statistical sense. 3I Atlas has an eccentricity of roughly 1.03, hyperbolic, unbound. Its velocity at infinity relative to the Sun is around 58 kilometers per second. That velocity, combined with the direction it's coming from, allows dynamical astronomers to calculate its motion through the galaxy. Multiple independent analyses by Hopkins, Taylor, Seligman, Alarcon, and Minev all converge on a thick disk origin with a dynamical age of 3 to 11 billion years. The thick disk orbits the galactic center with higher velocity dispersion and different kinematics than the thin disk where the Sun resides. Thick disk stars have lower metallicity, around 40% solar on average, and formed during the early epochs of galactic evolution. If 3I Atlas was ejected from a thick disk planetary system billions of years ago, it's been wandering the galaxy ever since, occasionally passing through molecular clouds, star-forming regions, supernova remnants, exposed to cosmic rays and interstellar UV radiation the whole time. That kind of history leaves scars. The comet we're seeing now is what survived. The close approach to Mars on October 3rd gives a rare opportunity. Mars Express and ExoMars TGO will observe with multiple instruments: thermal infrared imaging, UV spectroscopy, high-resolution imaging. They'll be looking from a different angle than Earth-based telescopes, potentially catching views of the night side or pole-on aspects we can't see. If there are jet structures or active regions on the nucleus, Mars observers might resolve them. After perihelion, assuming 3I Atlas survives without fragmenting, it will be on the outbound leg. By December, it's visible again from Earth, but already cooling, activity declining, volatiles exhausted. The spectroscopic opportunity is now, in August through October, while the comet is still heating up and venting material at high rates. 2. Borisov showed outburst activity and possible fragmentation as it passed perihelion. 3I Atlas is smaller, potentially more fragile. If the nucleus has weak structural integrity or internal pressure builds from rapid sublimation, it could shatter. Hubble will monitor for breakup signs. So far, as of August, observations show no outbursts or sudden brightness changes. Activity appears steady, smoothly increasing as solar distance decreases. That's a good sign. A steadily active comet is more likely to survive perihelion intact. but there's no guarantee. If it does fragment, we'll get a different data set. Exposed interior material, fresh surfaces, maybe different ice mixtures from deeper layers. If it stays whole, we'll track it outbound and compare the inbound and outbound chemistry. Either way, science wins. The comparison with one-eye Oumuamua is instructive. Oumuamua showed no coma, no tail, no detectable outgassing. It tumbled through the solar system like a dead rock, maybe with some slight non-gravitational acceleration that sparked endless debate about whether it was venting something too faint to detect. Its spectrum was red, its shape apparently elongated, its behavior bizarre. We learned almost nothing about its composition because there was nothing to spectroscopically analyze. 3-eye Atlas is the opposite. Bright coma, clear outgassing, detailed spectroscopic measurements, production rates with error bars, isotope ratios, molecular inventories. This is what we needed. A chemically active interstellar visitor that lets us actually measure what it's made of. And what we're measuring is unexpected. Lisa's SphereX paper, submitted August 21st, revised August 24th. Jewett's Hubble size, constraints, and optical characterization published in late July. Xing's swift UV observations detecting OH radicals published in early August. Kurita's near-infrared spectroscopy from Gemini South and IRTF showing water ice absorption published in late July. Yang's optical and near-infrared ground-based spectroscopy. Every dataset gets cross-referenced, combined, modeled. The JWST observations provide the gold standard for gas composition. SphereX confirms the CO2 dominance and adds spatial extent. Hubble constrains the nucleus size and provides high-resolution imaging. SWIFT gives UV emission lines for hydroxyl, inferring water photolysis rates. VLT adds nickel and cyanide detections. JCMT adds hydrogen cyanide. IRTF adds complementary near-infrared spectroscopy. Each instrument covers a different wavelength range or spatial scale, and together they build a complete picture. Detected by the VLT's UVES spectrograph on August 23rd at 2.85 AU from the Sun. Atomic nickel emission lines in the UV, not just 3-eye Atlas. 2-eye Borisov also showed nickel emission. In fact, nickel emission is more common in comets than previously thought. But the levels in 3-eye Atlas are high for a comet this far from the Sun. Nickel tetracarbonyl hypothesis explains it. If dust grains contain NiCO4, that molecule is extremely volatile, sublimating even at low temperatures and breaking apart under UV light to release atomic nickel and carbon monoxide. That would boost both nickel emission and carbon monoxide production, without requiring the nucleus to be close to the Sun. It's a surface chemistry effect. Cosmic ray irradiation, or UV processing, in interstellar space could create nickel carbonyls on grain surfaces. As the Sun heats the coma, they decompose, releasing nickel and CO. The cyanide detection on September 7th adds another layer. Hydrogen cyanide, HCN, is a common cometary volatile. A production rate of 1.5 times 10 to the 25th molecules per second at 2.33 AU is consistent with typical comet activity. HCN forms in the coma from photolysis of more complex organics or directly sublimes from the nucleus if present as ice. Either way, it indicates organic chemistry is happening. Carbon-rich dust, silicate grains coated in organics, refractory material from the nucleus surface. The data doesn't constrain it yet. What we do know, the dust is optically thin at JWST wavelengths, meaning light passes through without much absorption, so the coma isn't dense with large particles. The dust-to-gas ratio, inferred from comparing continuum brightness to gas emission line strength, suggests modest dust production relative to gas, 12 to 120 kilograms per second dust mass loss rate from early estimates. That's within normal range for small, moderately active comets. The dust tail is developing. Hubble images from July 21st show a faint tail streaming away from the nucleus. By August, ground-based imaging from Gemini South shows a clear dust tail and hints of a gas tail. The solar wind and radiation pressure are sculpting the coma into classic cometary structures. As 3-eye Atlas approaches perihelion, those tails should grow more pronounced. At 3.3 AU, solar flux is roughly 9% of what Earth receives. Blackbody equilibrium temperature for a dark object with low thermal inertia is around 180 to 200 Kelvin at that distance. Water ice sublimation becomes efficient above 170 Kelvin, so water should be starting to vent, and it is, weekly. Carbon dioxide sublimes efficiently from 60 Kelvin up, so CO2 has been outgassing vigorously since much farther out. TESS observations from May 7th to June 3rd, 2025, show 3-eye Atlas was already active at 6.4 AU, where temperatures are far below water sublimation. That early activity confirms the dominance of supervolatile ices like CO2. Carbon monoxide sublimes at even lower temperatures, yet CO production is low. That discrepancy is the puzzle. Either the nucleus has very little CO ice left, or it's trapped beneath a layer that doesn't allow it to escape, or it was never abundant to begin with. The data leans toward already lost, or never had much. A comet that spent billions of years in interstellar space at roughly 4 Kelvin, occasionally passing through warmer regions near star-forming zones, or getting irradiated by nearby stellar flares, could easily lose light volatiles over geologic timescales. Predictions vary. If the nucleus crust is thick and insulating, water production might remain modest even at 1.4 AU with CO2 continuing to dominate. If heat penetrates and water ice sublimates strongly, we could see a dramatic shift in Coma composition, a large water envelope forming, dust production spiking, maybe an outburst event. The analogies to Hartley 2 and to C2016 R2 both suggest continued CO2 dominance with water as a secondary component, but we won't know until October. The Mars spacecraft observations will provide near real-time updates. If the comet survives and brightens, ground-based observers will track it through perihelion passage. If it fragments, the spectroscopic data will be chaotic and fascinating. The ESA SOHO Solar Observatory will have 3I Atlas in its field of view during solar conjunction. SOHO's coronagraphs block the sun's disk and image the immediate corona. Many sun-grazing comets have been discovered in SOHO data. 3. I-Atlas isn't a sun-grazer's, it stays too far out, but SU might catch it if it's bright enough, providing a unique view exactly when Earth-based telescopes are blind. If 3I Atlas comes from a thick disk star, that star likely had lower metallicity than the sun. Heavy elements, carbon, oxygen, silicon, iron, nickel, would be present but at reduced abundance. How does that affect comet composition? Protoplanetary disks around metal-poor stars have less dust and fewer refractory elements. Ice-to-rock ratios might differ, carbon and oxygen abundances relative to hydrogen shift. If a disk has 40% solar metallicity, you still get water ice, carbon dioxide, carbon monoxide, organics, all the usual volatile ices, but the dust content, the silicate to ice ratio, the abundance of metals like nickel and iron, those could be lower. Yet 3I Atlas shows nickel emission. It has dust. The carbon isotope ratio is solar-like. Maybe metallicity doesn't dramatically alter cometary chemistry in this mass range. Or maybe 3. I-Atlas formed around a star that happened to have near solar carbon and oxygen, despite being metal-poor overall. Stellar abundances vary. Thick disk stars aren't uniformly low metallicity. They span a range. Without knowing which specific star ejected this comet, we're guessing. Ejection mechanisms matter. Giant planets fling comets into interstellar space through gravitational encounters. In our solar system, Jupiter and Saturn are the main ejectors. Encounters between a comet on an eccentric orbit and a giant planet can boost the comet's velocity past escape speed, sending it outward forever. The same process happens in other planetary systems. Young systems with giant planets in the process of migrating inward or outward, dynamically interacting, clearing their surroundings, eject vast numbers of small bodies. Stellar encounters can also do it. If two stars pass close enough, their gravitational influence can strip comets from each other's outer reservoirs, or a close binary star system can eject objects through three-body interactions. The ejection imprints a velocity distribution. Most ejected comets leave at relatively low excess velocity, just barely unbound. A few get kicked hard and leave at high speed. 3I Atlas, with 58 kilometers per second excess velocity, is on the high side, suggesting a strong ejection event. That could mean a close encounter with a massive planet or a stellar flyby. At any given moment, interstellar space contains more rogue planets, comets, and asteroids than exist bound in star systems. The Milky Way is full of orphaned objects, and they vastly outnumber the bound population. We only notice them when they happen to pass through the solar system, and only then if they're bright enough or close enough to detect. The estimated rate of interstellar object passages through the inner solar system is maybe 1 per year larger than 100 meters diameter. Smaller ones come through constantly. Most are dark, inactive, and zip past unnoticed. 3I Atlas is a lucky find, large enough to show a coma, active enough to be bright, discovered by a dedicated survey, observed by the most powerful telescopes we have, and chemically bizarre in a way that demands explanation. It got gravitationally ejected early, possibly by a giant planet or stellar encounter, and spent 3 to 11 billion years traveling through interstellar space. During that journey, cosmic ray irradiation and occasional passages through denser interstellar regions thermally processed its surface, creating a cooked shell rich in CO2, depleting light volatiles like carbon monoxide. The nucleus today is small, less than 3 kilometers, with a thick insulating crust that inhibits heat penetration and suppresses water sublimation relative to CO2. As it approaches the sun, the crust heats, carbon dioxide sublimates vigorously from shallow depths, and water remains mostly locked below. The result? A coma dominated by carbon dioxide at 7.6 to 1 over water, one of the most extreme ratios ever measured. The spectroscopic data from JWST, SphereX, and other instruments document this composition in unprecedented detail, providing a chemical fingerprint of planetary formation in another star system, and offering insight into how comets evolve over billions of years in the void between stars. October 27th, 1.4 AU. If 3I Atlas survives perihelion intact, it will begin the long journey outward. By November, it's beyond Mars' orbit again, cooling, slowing its outgassing. By December, it's visible from Earth for a final round of observations before it becomes too faint and distant. Hubble will watch for late activity or fragmentation. JWST will capture one last spectrum to compare with the inbound data. Did the composition shift? Did water ramp up? Did new molecules appear from deeper layers? By January 2026, it's out beyond Jupiter's orbit. Activity shut down, coma dissipated, back to being a frozen rock flying through space. The hyperbolic trajectory carries it out of the solar system at over 50 kilometers per second relative to the sun. In a few thousand years, it will be light years away, gone from our reach forever. The data we collected in these few months is all we'll ever have. Hard numbers. CO2 to H2O ratio 7.6 plus or minus 0.3. Carbon isotope ratio similar to Earth. Production rates 129 kilograms per second. CO2 6.6 kilograms per second water, 14 kilograms per second carbon monoxide. Nucleus diameter probably under 1 kilometer. Coma extending 348,000 kilometers. Dust mass loss 12 to 120 kilograms per second. Age 3 to 11 billion years. Thick disk origin. These are facts. Documented, peer-reviewed. Published with error bars and calibration checks. This is what separates speculation from science. We didn't guess, we measured. JWST spectra, SphereX photometry, Hubble imaging, Swift UV detections, VLT nickel emission, JCMT hydrogen cyanide, each instrument adding a piece. Each dataset independently confirming the core finding. This interstellar comet is CO2, dominated, water-poor, chemically processed, ancient, and fundamentally different from the comets we've studied for centuries within our own solar system. It's a sample return mission we didn't have to launch. A pristine chunk of another planetary system delivered to our doorstep, carrying ices and organics that condensed around a different star, carrying scars from a journey through the galaxy lasting longer than Earth has existed, carrying chemistry that reveals how planet formation works under conditions we can't easily observe. The James Webb Space Telescope gave us the most detailed chemical inventory ever obtained for an interstellar visitor. The carbon dioxide dominance is the headline, but the full picture, the CO ratios, the water ice presence, the dust properties, the nickel and cyanide, the isotopes, all of it together paints a portrait of deep time and deep space. A comet born in the thick disk of the Milky Way, ejected in youth, aged in darkness, now passing through our neighborhood, venting gas, leaving a trail, giving us this one chance to understand what lies beyond the edge of our own cosmic cradle. Martin Cordner's paper hits ARXIF, revised August 29th, final version September 10th. The abstract ends with an understated line. Further observations at distances less than 3 AU will be needed to facilitate measurement of the bulk nucleus composition as it passes closer to the sun. Translation: we need to keep watching. The story isn't over. Perihelion is coming. The comet might fragment, water might surge, new volatiles might appear, or it might stay stubbornly CO2 dominated all the way through, proving the thermal insulation hypothesis. Either outcome teaches us something. Science doesn't demand a particular result, it demands measurement. And for 3I Atlas, the measurements are in carbon dioxide, 7.6 to 1, dominating the coma, rewriting the book on interstellar visitors. The receipts are on the table.